Within this demonstration, we'll look at a catalyzer used for converting component A within an exhaust gas into component B. The gas flows through a number of channels N, where the channel walls are covered with a reactive layer used for conversion from component A to B. The geometric characteristics are given, as well as the inlet mass fraction and diffusion coefficient, and the properties of the exhaust gas. Furthermore, within the hints it's stated that the mass fraction of A at the channel wall is 0. At the inlet there is no component B present. Components A and B have the same molecular weights. The flow is fully developed. The surfaces are isothermal. Material properties are constant. There is no back diffusion of substance B, and mass diffusion along the radial direction of the channel is negligible. For the first task, the mass transfer coefficient must be calculated using the analogy between heat and mass transfer. Furthermore, all characteristic numbers and equations must be provided as well. With the analogy between heat and mass transfer, Lewis' law is meant, which is applicable for a large portion of gases where the Lewis number is equal to 1. For this case, the Nusselt number function and Sherwood function have an identical solution form and can be rewritten from one into another. The given problem can be classified as forced internal convective flow within a pipe. To determine the heat transfer correlation that is applicable, the Reynolds number must be determined, and therefore we first need the average fluid velocity. Since we have a number of channels, we first have to divide the mass flow by the number of channels that we have, and then we can divide the remaining mass flow by the density of the fluid and the cross-sectional area through which it's flowing. Now we have an expression for the average fluid velocity, and so we can determine the Reynolds number by substituting this velocity. And by filling in all numbers, we find a value of about 5030. So it turns out that we're in the turbulent regime. The ratio between the length and diameter of our channel is 150, which is larger than 40, and therefore we can make use of heat transfer correlation 15 of the book of formularies. This correlation can be rewritten to a Sherwood number function by substituting Sherwood for the Nusselt number and the Schmidt number for the Prandtl number. So before doing these calculations, we have to determine what the Schmidt number actually is. And by using the definition of the Schmidt number and substituting all numbers, we find a value of about 0.4. So if we rewrite the Nusselt number function into a Sherwood number function and substitute all numbers, we find a Sherwood number of 18.2. And by rewriting the definition of the Sherwood number, plugging in all numerical values, we find a mass transfer coefficient of 0.28. So by using the analogy between heat and mass transfer, we have determined the mass transfer coefficient. In the second task, we are asked to derive the differential equation that governs the evolution of substance A along a catalyst channel in the axial direction. This equation is derived from setting up an energy balance around a one-dimensional infinitesimal element in the axial direction. In the axial direction, we have an effective flow entering and leaving the element, while at the same time, component A is transferred to the catalyzer wall by diffusion. So mass transport is governed by advection in the axial direction and diffusion between the wall and the fluid. And then the next step is finding a definition for each term. The incoming rate of component A due to advective transport used from the mass flow rate for that specific channel, as well as the mass fraction of component A at that position. Since we're working with an infinitesimal element, we can approximate the outgoing component by use of the Taylor series expansion. Then we would find the following. And lastly, the outgoing rate of mass diffusion can be determined from the mass transfer coefficient that we've determined previously. And then if we insert all definitions into the balance, we find the following differential equation that governs the evolution of component A in the axial direction of the channel. In the third task, we are asked to determine the functions that describe the mass fractions of component A and B in the axial direction. These functions result from solving the previously determined differential equation. Since in this equation the mass fraction had been differentiated once with respect to x, we need one boundary condition. Within the task description, the inlet mass fraction is given, which we can use to define the boundary condition at x equals 0. To solve the equation, we have to rewrite its form and substitute the mass fraction at the catalyzer wall, which is 0, and if we do this, we get the following expression. And then the next step is integrating both sides of the equation. We're working out this integral expression leads to the following exponential function describing the mass fraction of component A. Furthermore, at the inlet only component A was present, and component A is converted into component B. The sum of the mass fractions of A and B must be equal to the inlet mass fraction of component A. We can use this relationship and rewrite it to find the mass fraction of component B. Then we find this exponential function for component B. So by solving the differential equation and making use of the conservation of mass, we found two expressions describing the mass fractions of component A and B in the actual direction. Then, in the fourth task, we are asked to draw the mass fraction profiles along the channel length for a channel that is infinitely long. We will start with that of component A. If the channel is infinitely long, at the end the mass fraction will be 0, and the profile must gradually approach this since the reaction speed decreases due to less particles of A being present, so we will have a horizontal slope at the end. At the inlet, it must be equal to the inlet mass fraction of component A, and the slope will be the steepest since here we have the highest conversion from A to B due to the most particles of A being present. So in between these 2 points, the slope of component A gradually has to decrease. For component B, at the end of the channel, the mass fraction must be equal to the inlet mass fraction of component A, since here it all has been converted into component B. Just like component A, the slope must be horizontal, since no reactions are taking place anymore. At the beginning of the channel, no component B is present, and therefore the mass fraction of B at that location is 0. Just as for A, the reaction rate over here is the largest, and therefore we have the steepest slope. So as we already saw in task C, the profile of component B is the mirrored version of component A. So even without having any information on the mathematical functions, we were able to sketch both mass fraction profiles. Then in the last task, it appeared that the outlet mass fraction of component A is too high. For this reason, the catalyzer must be redesigned, and we have to change the number of channels to make the design such that it meets the desired outlet mass fraction. So if we recall the derived expression for component A and we plug in x is equal to L, we find the outlet mass fraction. We can directly see that the number of channels affects this mass fraction. However, the mass transfer coefficient also depends on it since it is affected by the Reynolds number. And therefore, the mass transfer coefficient has to be expressed in dependency of the number of channels. So previously we already determined this expression for the mass transfer coefficient. And then if we plug in the definition of the Reynolds number, we get the mass transfer coefficient expressed in the number of channels. So if we insert this into the definition of the outlet mass fraction and make the number of channels free, we get the following expression. And then we can fill in all numerical values and we find the following. So by simply rewriting the function of the mass fraction profile that we previously derived, we found an expression for the number of channels as a function of the outlet concentration.